Okay, for the next unit, we're going to look at how to calculate the heat involved in physical changes. We will get to chemical changes in the next two videos. So to begin with, let's review. What is a physical change? A physical change is a change that does not alter the chemical composition of the material. So for example, if you change the state, if you melt something or boil something, that's a physical change. If you dissolve something in water, that's a physical change. That substance is still there and you can get it back. It didn't alter what that substance is actually made of. So those are the things we're going to be focusing on, changing states and dissolving, and the heat that's involved in those two processes. So when we talk about states of matter, we're really looking at the kinetic energy that's involved in those states of matter. The kinetic energy is energy an object has because of its motion. And all particles are in motion of some sort. It just depends on how much energy they have, what their heat is, as to how much they're moving. So we're going to be looking at the kinetic energy of the solid, liquid, and gas phase. So to compare the states, if we start with gases, gas particles have very high energy. They move very quickly and there's lots of space between them. When gas particles collide with the container, that's what causes pressure. So when you think about gas pressure, the more particles there are, the faster they're moving, the more collisions, the higher the pressure. And because those particles are so far apart, there is no attraction between them. Now when gases turn into liquids, basically that means they now have lower energy. They're still moving so they can flow past one another, but they're a lot closer together. The particles are attracted to each other through intermolecular forces. And then if you lower the temperature even more and turn that liquid into a solid, now the particles have very low energy. They're still moving, but this time they're vibrating. They're not moving around each other. They are tightly packed and organized, but they still have some movement. They are vibrating around a fixed point. So when we put all of that information together, we want to look at what's called a phase diagram. Now this example is specifically for water, and every substance has its own phase diagram. And on the phase diagram, as you can see, the solid phase is over here on the left, the liquid phase is in the middle, the gas phase is on the right, and they all have the same general Y shape. Some of them are, tilted one way or the other, a little bigger, a little smaller, depends on the substance, but they all have the same basic shape. The y-axis is going to be pressure, and the units of pressure that we're going to use are atmospheres, and the x-axis will be temperature, and this temperature is in degrees Celsius. Now there are a couple of points that you can pay attention to on a phase diagram. One of those is called the normal melting point, and that word normal means the melting point at standard pressure. Standard pressure is defined as 1 atmosphere. So you can see at 1 atmosphere, that would be the normal melting point, the point at which this particular substance melts. And we know for water, that's 0 degrees Celsius. The normal boiling point is the temperature at which a substance boils at standard pressure. So at 1 atmosphere, if we come over here, this is the standard or the normal boiling point, which we know happens at 100 degrees Celsius. And then the triple point is very unique. It is the only set of conditions at which all three phases can exist in equilibrium with each other. And that is way down here at the bottom. If I can get my cursor to work, here it is, way down here at the bottom where the lines intersect. That's the triple point. So at that temperature and that very low pressure, you could have ice and water and water vapor all in the same container all at the same time. So there's only one set of conditions at which that can happen. Now, if we look at changing from one phase to another, when you cross over this line right here, you can change from a solid to a liquid or a liquid to a solid. So we can see how changing the pressure affects the melting point of water. Okay, if we lower the pressure, it's going to melt at a higher temperature than 0. If we increase the pressure, it'll melt at a lower temperature than 0. So any point along this line, at whatever pressure we have, we could turn a solid into a liquid. Same thing applies for this line. Any place that we cross that line will be considered a boiling point, And if we change the pressure, then we can change the temperature at which water boils. So at very low pressure, we could have water boiling at 50 degrees Celsius because the pressure is so low. So anywhere that you cross that line would be considered a boiling point. Now let's define these phase changes. When we change from a gas to a liquid, we call that condensation. From liquid to gas, we call vaporization. When we change from a liquid to a solid, that's freezing or solidification. And from solid to liquid is called fusion, which is also considered melting. And then there are some special phase changes. We can actually go directly from a solid. Where's my cursor? Here we go. We can go directly from a solid to a gas, which is called sublimation. And I know you've all seen this happen before. Think about dry ice. Dry ice goes directly from solid carbon dioxide to gaseous carbon dioxide. It doesn't melt first, so carbon dioxide goes through sublimation. The opposite of that would be considered deposition. So those are all of the terms for our phase changes that we could look at on our phase diagram. Okay, so let's get to the heat involved in these phase changes. There are two things we need to define. One is called the molar heat of fusion, so we're going to use delta H for heat, FUS for fusion. It's the heat absorbed by 1 mole of a substance in melting from a solid to a liquid. Every substance has its own heat of fusion. We also have a heat of vaporization, which is delta H VAP for vaporization. It's the amount of heat necessary to vaporize 1 mole of a given liquid. Every substance has its own heat of vaporization. And these are all in your book on page 308. So there's a chart of heats of fusion and heats of vaporization, and we're going to be using those quite extensively. Now, if you'll notice in the chart, the heat of fusion is equal to the negative heat of solidification. So you're not given the heat of solidification because it's equal to the heat of fusion. It's just a negative value. So it's heat that's released rather than heat that's absorbed. Same thing with heat of condensation and heat of vaporization. They are equal in amount, they're just opposite in sign. So we're going to use that chart on page 308. So if you have your book handy, you might want to open it up. All right, let's look at an example. How many grams of ice at 0 degrees Celsius in 1 atmosphere could be melted by the addition of 2.25 kilojoules of heat? So the first thing we want to do is look at our chart and find that for water, that's what ice is, the heat of fusion, which is melting, right? The heat of fusion for water is 6.01 kilojoules per mole. Okay, so this now becomes a conversion factor. So we're going to use dimensional analysis to solve this problem. So we're going to say 2.25 kilojoules over 1. We use our heat of fusion as our conversion factor. So for every 1 mole of water, it takes 6.01 kilojoules to melt it. And now the question asks how many grams. So our kilojoules have canceled. How do we convert from moles to grams? We use the molar mass. So the molar mass of water is 18 grams per mole. You get that from the periodic table. So when we do that math, we end up with 6.74 grams of ice. If we had 6.74 grams of ice, it would completely melt by the addition of 2.25 kilojoules of heat. So you're going to use your heat of fusion or your heat of vaporization as a conversion factor in your calculation. Which brings us to something called the heating curve. And a heating curve, yes, I know it's not curved, is kind of a stair-step graph that shows us as the temperature changes and as we add heat, how do we go from solid to liquid to gas? Now you'll notice that we have flat parts of our curve at the melting point and at the boiling point. Those flat points represent the amount of heat needed to change from solid to liquid. We call that the delta H of fusion. We just defined it. And then the amount of heat needed to change the liquid to the gas at the boiling point is the delta H of vaporization. Okay, so those parts of the graph, we would use our two new conversion factors to figure out the heat involved. Now, on the parts of the graph that increase from low temperature to higher temperature, okay, so stopping at that point right there, here we would have to use our formula delta H equals Cm delta T to figure out the heat involved. Same thing, from this corner to this corner, as we raise the temperature of the liquid, we would use delta H equals Cm delta T, and then again, from this corner up, use the formula delta H equals Cm delta T. So when you're using a heating curve, you are either increasing the temperature or changing the state. Increasing the temperature, changing the state, increasing the temperature. So technically, if we were going to do this problem and we wanted to know how much heat does it take to get ice from way down here to water vapor way up here, we would have to do 1, 2, 3, 4, 5 separate calculations and then add all of those heats together. And that's what we're going to work on in class together.